Hello, this is my assessment for balanced search trees. I'm going to start with question 1. Consider the worst possible insertion order for 10 strings, each with 3 characters long, into a ternary search tree. What is the height of the tree after these insertions? So in this case, string values are made by connecting nodes as characters. The worst case is going to be when all the characters are greater than or less than the root, which would make the tree very spindly. The height is going to end up being 11 in a worst case scenario, because there are 9 edges between the unselected characters, and then there's 2 between the 3 selected characters. In a binary search tree, all the values are held as strings in each of the nodes, so they form a linked list like that, or like a linked list. The worst case height is going to be when all of the strings are greater than or less than the root value, the same as a TST. Tree is also going to be very spindly. The max height of a binary search tree is equal to the levels minus 1, so the worst case height is going to be 9. Here's some corresponding trees. What is the height of the corresponding 2-3 tree? The red edges don't count as an additional level because they're going to get to be stuffed. So if we look at this, you can see I've diagrammed out how the topmost red edge has level 1, 1, and then the next level is 2, and the next level is 3. On the right side, it goes to level 2, and then it's level 3, and then the last level is a red edge, so you don't count that. The height is going to be the levels minus 1, so that is 2. How many values do you need to add to the corresponding 2-3 tree in order to cause a height increase? The minimum nodes in a level is 2 to the power k minus 1, where k is the level. The current level is 3, so k is going to be 4 in order to raise to the next height. 2 to the 4th power minus 1 is 15. Currently there's 12 nodes, so 3 more nodes are going to be required to cause a height increase. The way that this will look is you're going to keep overstuffing the right side of this tree until the root node must push a value up to a new level. So you're going to stuff that red edge first, and then you're going to stuff above it, and then you're going to stuff above that. And after you stuff all of that, the top is going to have 3 values that it must push up 1, and that'll give you a height increase. How many values can you add to the corresponding 2-3 tree without causing a height increase? Max nodes containable by this level is 3 to the power k minus 1. If every node is stuffed with 3 nodes on the second level and 9 nodes are on the third, then there will be a maximum of 26 at the current height. There's currently 12 values, so you can add 14 more before the height has to increase. How many values do you need to add to the left-leaning red-black tree in order to cause a height increase? You can just add 1 value to any of the 4 bottom left nodes, and it'll cause a height increase. If you did it to the right side, it's either going to add to an existing level or there's going to be a rotation. What happens when a new element with a value greater than all other elements is added to this tree? In this case, if it's bigger than everything else, it has to go furthest right, and that breaks the invariant of the tree, so you have to perform a rotate left in order to keep things good, because a left-leaning red-black tree is unique, has that invariant to it. So the result is going to be that we insert a red edge right leaf hanging off the rightmost branch to represent the element, and then we rotate left on the new leaf's parent node.